Right, so this is chapter 8. Good evening, everyone. This is chapter 8, so it is just going to be short and sweet. We only have how many pages? 3 pages. Right. So on the grind, I want to you to understand this. On the grind, we are not looking at multiple problems, but we are looking at the concept. Okay. So you're not going to be expecting more problems being thrown at you. That's not going to work. But the only thing that you will find is the concept, how to answer the problems that you will face under that chapter. Okay. So this is chapter 8 integration, right? So we're going to look at the basics of integration. Okay. So the basics, I'm just going to cover the basics, right? I'm just going to build on that's what you did on MATH141. Right. So when you see a square root on your integration, right? So surely you will have to use the U substitution, okay? If it is an antiderivative, right? You're going to use a U substitution, but you will have to change the bounds if only that's going to be the definite integral. Okay, because if you have the bounds, maybe there's going to be x is equal to 2 all the way to x is equal to 3. If you make your u to be something else, you're changing the variable right now. You're not longer working with x, but you're working with u. So you will have to change the bounds, okay, because you're no longer working with x. All right. So what is happening here? All right. So about this problem, this is a common problem that you will find when you're introduced to integration, right? So right over here, as you can see, I've made a point right there that you have to simplify and reduce. So let us say maybe you don't know how to solve this problem. And then, okay, cool. Now, when you look at the problem, the only thing that you will want to do is to simplify the problem or what is this word? Factorize. Okay, but you will have to reduce it. Okay, if you see that you can, it is possible to reduce, you'll have to reduce. So right over here, you see that 4x minus 10, I can take out 2 because right over here, 2 is not going to be a problem because I can put away 2 right over here and put it outside. Okay, 2 is not a problem. And then right over here, this thing is fully reduced. It has been reduced. Okay, so it is no longer complex, but it has been reduced. So that's what you'll have to do. And then right over here, I see that, oh, okay, there is a square root. I'll have to use a U substitution. But now, then there's no need to change the bounds because this is not a definite integral, but it is an indefinite integral. Okay, so there's no need for that. So right over here, when you see a problem that it is possible to reduce it, please reduce it. You can break this, okay? Separate this and say 4x divided by this square root minus 10x divided by that square root. That's going to be a recipe for a disaster. Okay, do not do that. Try to reduce, and then after that, you're going to take it from there. Because about this problem, we have reduced that. We have 2x minus 5 in brackets. Take out 2 out of the integral. And then you'll have this. So right here, you can choose to separate, but there's no need for you to separate because that's the recipe for disaster. Look at the denominator. You'll have to use a U substitution. That's cool. But now, what is going to be your U? In this case, your U is going to be inside something that is inside the square root because the square root is your target. All right. So I have x squared minus 5x plus 6. Now, at this point, look at this. U stock, right? Try to use a U substitution because when you use a U substitution, probably the thing that you're going to do right over here, the derivative of U, is going to be the same thing that is right there on top. And that will definitely cancel out everything that is on the top because when you derive this and solve for dx, you will get du divided by 2x minus 5. And then you will have to cancel that. Okay? And then after that, you bring back everything you do and solve your integral. And then there is this thing right over here. So on the first problem, I talked about reducing. Okay, so right over here, we are just touching on the concept only, not the problems, the concept. Right. So I've brought some problems that are going to explain that concept. So right over here, if you can reduce, reduce it. And then you come back to this one. Now, if you look at this problem, let us say you don't know how to solve it. And then you have x squared divided by x squared plus 1. In the denominator, you'll be like, okay, my target is a denominator, right? So what I have to do is to derive, make my u to be x squared plus 1, or make my u to be x squared. Well, making your u to be x squared is not going to change anything. And then if you say your u is going to be x squared plus 1, well, probably if you derive that, it's going to give you 2x. Still is not going to cancel what's on the top. So you must have a strategy. So the strategy is to manipulate that by adding a 0. How do you add a 0? There is going to be a 1 minus a 1 because you're trying to accommodate this thing on the bottom. So right over here, if on the bottom you had plus 2, you're going to say, oh, this is plus 2 minus a 2. That's still a 0. Okay, so that's how you approach that problem, so that you will separate the variables, and then you will have x squared plus 1 divided by x squared plus 1 minus that 1 divided by x squared plus 1. You didn't change anything right here, but you just added a 0. Okay, you didn't change anything. And then when you proceed, you will see that, okay, fine, this is going to be 1. You can take the antiderivative of 1 minus, you have 1 divided by x squared plus 1. So above this is very important. You must know your tables, okay? You must know your tables, students, because right over here, the antiderivative of 1 divided by x squared plus 1, I guess that's going to be a ton of this, if not mistaken. You will have to know your tables because you can try and work this thing out and say maybe it's going to be in terms of x and what. It's not, okay? Try to understand and fully, completely remember your tables, okay? So that is for the basics of integration. Now, let's look at integration by parts. We did that a lot of time, okay? So we did integration by part, but what I'm going to emphasize, and just for those who just entered the grind later, I guess we'll have to look at the previous sessions for the integration by part. Okay, so about the integration by part, what I wanted to hash out is that you must choose the one that is better, right? So I'm just going to try and explain that right now with an example. All right, if you cannot, it's the other one. So remember that when doing integration by part, you will have to choose your u, you will have to choose your dv, right? Or your v. So in that case, it is important on what you're choosing because you don't have to mess with the integration by part. Okay, so about the example, I have example right over here, right? So I'm just going to write it real quick. We have an antiderivative of x ln of x dx, right? So on this problem, you cannot just choose right away. Okay, you must understand that, okay, fine, I have to choose something that's going to be better. What do you choose? It's your u. When you derive your u, it must be something that is better. And on the other hand, I must take the antiderivative of what is left. Okay, so in this point, if you choose a u to be ln of x, that's going to be better because the derivative of ln of x is going to be 1 over x. And then what about dv on this hand? Okay, dv is going to be equal to, oh, that's just going to be your x, right? Okay, that is pretty cool, right? That's cool. But now the problem is when you say, okay, my u is going to be equal to x, and then my dv is just going to be equal to ln of x. This is a problem because when you take an antiderivative of this, the antiderivative of ln of x, well, probably you might or might not know the antiderivative of ln of x. So do not make your life to be complex because you will have to do another integration by parts, finding the antiderivative of ln of x. Okay, so because right over here, if you cannot take an antiderivative, it's the other way around. So it's the other one, which means it's this one. So what I'm trying to emphasize here is that whenever you have ln of x on your integral, you must let that to be a u, okay? Unless if you know what's an antiderivative of ln of x, which is x ln of x, I guess minus x, something like that, minus or plus x, something like that. Okay, so this is what I wanted to emphasize about the integration by parts, okay? If you have ln of x, to make your life to be simple, let that to be a u, so that if you derive that, it's going to be 1 over x, and then you move on. Okay, unless we have a different problem. All right. So let's head down to the last page. Okay. Guess this is the last one. All right. So looking at the reduction formulas, right? So on the reduction formulas, I guess we have covered that on the grind, and I'm happy with that. All right. So I just provided you with the basics, right? Equations of this, but you'll have to prove this, which is very simple, but you will have to prove this. Okay, it's a must to know this. Okay, so about the advice, now listen to me carefully on this. There's a reason why I added the advice. Okay, so on the advice to be a good engineer, okay, the session is that it's on the session. So if you are going back to this note, you'll have to go back to the recorded session so that you can understand where is the advice, what is the advice. So at this point, the first advice is of the shortcut. Okay, so whenever you're doing the integration, you must be working with time because time is limited, right? So the advice that I'm going to give you on the shortcuts, probably you don't want a shortcut, but you must if you are out of time. So do you remember that when you have sine squared of x, right? What is that equals to? And then cos squared of x, what is that equals to? Right. So at this point, whenever you have the antiderivative of, okay, whenever you have an antiderivative of sine squared of x, okay, do not change that to be 1 minus cos squared of x because you haven't changed anything, okay? You will have to separate these again. You will have an antiderivative of cos squared of x, which is the same thing. You're going to go back to sine squared of x. So which is going to be a loop. You're going to go back sine. So that's just going to be a loop. But my advice is to change that sine squared of x, okay, relate that to this basic formula that says cos of 2x is going to be equal to cos squared of x minus sine squared of x, right? Because right over here, that would basically give us that cos of 2x, which is great, okay? We're not going to be working with the loop right now, but you're going to be working with that cos of 2x, okay? So at this point, you must try and change that sine squared of x in terms of that, okay? And then you will have to be on a good track with that. And then same applies to this one. Change that using that identity. Not that, okay, cos squared of x is 1 minus sine squared of x. It's not going to work. Okay, so you will have to change that to be like that. Then that's going to help you. All right. So moving on, I've got the second advice about the trig shortcuts. What about the trig shortcut? Okay, so on the trig shortcuts, I don't remember the trig shortcuts. Okay, I don't want to lie. Okay, oh, all right. About the trig shortcuts, probably it was that one that I made. But the other one, okay, do not be afraid to be a good engineer. What do I mean by that? So when you say, okay, let your session to be X, this is how you become a good mathematician or a good engineer. Okay, so whenever you're working with integration, you will see that this first part, you're going to be working with that all the way to your last problem. So when you've done your integration by part, you put a u multiplied by v, it's going to be that part. You're going to be done with that part. Do not be afraid to say, so that you're gonna save time, to say let all that to be I. That is great, but please say it that suppose that this is equal to I, or let this to be equal to I. So that you're going to have to say, okay, this is I plus and carry on. And then go back I plus. And then at the end of the day, you bring back what you had. Okay, not by writing negative 1 over n, no matter how fast you are, but you have saved a lot of seconds on that. Okay, that's a good advice that I'm going to give you. Do not be afraid to let something equal to something. Maybe, for example, if you have a big number multiplied by a variable divided by m times n, this is just a random example, right? So that big number, let that to be equal to z, okay? So that you would like zx divided by m times n. You're not going to say that number, that long number, multiplied by x. You can even make mistakes, but you'll have to let something to be equal to something. So that's going to be working. So that's going to work with a good time. All right. So that's just an advice part. Okay, we're moving on. All right. So right over here on the reduction formula, so if you have sine to the power n x only, you can use the reduction formula. Cos of to the power n x, you can use the reduction formula. But what about the multiplication of the two? So when you're multiplying the two, you will have to look at the exponents, right? So you have sine and cos. So if your m is odd, you will have to separate that. So right over here, our m is odd and we have sine x. So separate your sine x. Your n is odd, it's cos of x. You have to separate that cos of x. If they are both even, you will have to use the advice right over here, this advice that I gave you right here. Okay, if they are even, because you're going to be having maybe cos squared, right? Or even cos to the power 4, you can reduce that. And then use the advice. If you have cos of squared x, you have to change that to be in terms of cos of 2x, whatever. Okay, so that's the way it works. All right, and then moving on, about that tan to the power m multiplied by sec to the power n, this is the same concept as that one, but it changes. Okay, so about tan of m, if m is odd, this is what you will have to remember. Okay, if m is odd, you have to split tan, right? Split tan. And then if n is even, n is for sec. So what you have to do is to make that sec to be equal to 1 plus tan squared of x, and then you will proceed. But if they are both even and odd, not both, if m is even and if n is odd, that is important right over here. I don't know whether you remember that or not. This is wrong actually. But when m is even and when n is odd, okay, so what you have to do, you work with sec squared of x, which will be something that is right here on the bottom, right, on the top, which is going to be 1 plus tan of squared of x. Okay, you change sec squared to be 1 plus tan squared of x. And then along the way, you will have to use the reduction formula. Okay, you will see when doing the problems, you will have to use the reduction formula when working with that. So these notes are there if you got stuck, but you have a problem where you have tan and sec together, you will have to use these notes and see where do I get the clarity. And then after that, you're going to be able to go. All right. And then these are the useful formulas, right? The identities. Okay. So probably some of you didn't know these identities. The only thing that I'm going to give you is that you must know that cos is a king and sine is an intruder, right? So what do I mean by that? So whenever you have cos, everything is positive, we're good. But whenever you have sine, we must have something that is negative because there is no longer a cos. Look at this right over here. If you have cos of b, we're good because there is a cos, so we have a plus right there, right? Everything is positive. And then if you have a sine, there's no cos right here. Sine is an intruder. So what do you have to do? You put a negative. I nearly put a plus, but it's a negative. I just remember that. Okay. Right over here, we have cos only. We have a plus as well. Okay. So that's pretty simple. But the only thing that changes right over here, since you have cos, you must have a cos and a cos right here. On the top, the first one, since we have sine A and cos of B, you must have sine and sine because you started with the sine. Okay, so right over here, you have sine of A, sine of B, cos is not there, intruder, you have a negative. But inside, you're going to have a cos and a cos. So cos is a king. That is why I'm saying that. If you want to have a discussion on that, well, I'm going to beat you on that one. But it really goes down to the derivative as well of cos of x, right? So the derivative of cos of x is negative sine of x. Why is it negative sine of x? Because there is no longer cos. There is a sine. So sine is an intruder, goes with a negative. But I'm not there. This is just my own theory. Okay. Now this is the most fun part, right? We are at the end. The partial fractions. So I guess you have been introduced to the partial fractions. We're not going to do the partial fractions on this session, okay? But we're going to do them, I guess, tomorrow along with 142, the partial fractions, because I couldn't take that anymore. I'm not that well, so I was not okay. I'm going to just introduce the partial fractions since you know very well that what are partial fractions and all that. I'm going to just introduce you using the baby step way, okay? That's just an introduction. What is happening? Okay, so right over here, I've got an example using the numbers only. We're not going to be using A and B's and all that. Okay, so I've got an example. We have, let us say we have 1/3, okay, and plus what? Plus 1/4. Right. So if you try to solve this, right, let us say you are in primary, you're trying to solve this. So the only thing that you have to do, you'll be like, okay, I'm going to multiply this and then cross multiply that. Okay. So 3 times 4, that's going to be a 12. And then 3 times 1, 4 times 1 is going to be a 4 plus 3 times 1, there's going to be a 3. And then at the end of the day, you will have your 7 divided by 12. So this is the answer that you have right here. On the partial fractions, we are getting the answer. We want to go back to that. Okay? That's the partial fractions. You have the answer, you're going back to what you had before you have that answer. Okay? So it is going to be something like that. But the most important thing that I want to highlight, probably I'm just introducing the partial fractions. You will have to look at the linear factor first before you separate, and you'll have to look at your quadratic expression, right? The quadratic expression before you separate everything. Look at what you have. So when you separate, look at what you have. Do you have a linear factor or a quadratic expression? And then after that, you're going to take it from there. But this is an introduction of the partial fractions with the baby step, okay? Not with the hard part where you start with an A's and all that, start with the hard problem. But using the numbers only, you understand the concept of the partial fractions, okay? We got the answer 7/12. What did we had from the beginning? We had 1/3 plus 1/4. How can I get that? Okay, use the partial fractions. Thank you so much. Any questions? Right. So if there are no questions, I'm just going to post this on the grind as along with the notes, and then tomorrow we're going to proceed to 142 as well as the concept for the partial fractions. Thank you.